Okay, great, thank you. Yeah, so feel free to use the chat to ask questions. Maybe somebody else can yell out those questions to me because I can't monitor the chat while I'm giving the talk, but I don't mind being interrupted. So if someone has a question, please feel free to just interrupt me and ask the question. Okay, yeah, so today I'm going to be talking about classical algorithms for correlation, and this is joint work with Sergey Ravi and David Gossett. So let's just get into it. So what is correlation? It's simply the correlation between some Boolean function f and the Fourier transform of another Boolean function g. And so this is sort of the, why it's called correlation, because it's got the combination of this word correlation and correlation. And I've written out the correlation here of f and g just in terms of the sum over inputs to f and g. But I think for many of you, it'll perhaps be more natural if I describe the quantum circuit which gives rise to this quantity. So let's do that. So you start in the superposition of all computational basis states. You apply the sort of irregularization of the Boolean function f. So this is simply the unitary that on the computational basis state x applies f of x into the phase of the state. Then you apply a layer of Hadamard. So this is sort of what's doing the work of the Fourier transform here. Then you apply the irregularization of the Boolean function g. You apply another layer of Hadamards, and you consider the amplitude on the all zero state. And it's not so important that you sort of followed all the lines of the algebra there on the right. But what you see is that you have this transition amplitude in this nice simple quantum circuit equal to the correlation that we wanted to compute. So this is our running definition of correlation, and we can define a problem based on this quantity. So given Boolean functions f and g, the problem is to estimate their correlation to some added accuracy epsilon. And so one of the points that I want to make on this slide is that in some sense, correlation is one of the hardest problems that can be solved efficiently by a quantum computer that can't be solved efficiently by a classical computer. So correlation was initially defined in the context of quantum query complexity. So this is not a quantum query complexity talk, but I would sort of be remiss if I didn't bring it up here, since that was how it sort of originally came to being. And so quantum query complexity, or query complexity more generally, is a model of computation where you're not charged for sort of the normal resources like space or time, but rather you're charged for the number of times you access some oracle. And for our purposes, the oracles here are going to be the functions f and g. So how many times do you access the functions f and g? And we saw in the previous slide that there was this nice simple quantum algorithm to compute the correlation with only two queries, like one to f and one to g. But actually, there's some sort of clever way that you can combine these oracles together so that there's sort of one oracle that contains both the information of f and g inside of it. And then this quantum algorithm can be reduced to exactly one query to that oracle. But on the other hand, Aronson and Bynus show that any classical algorithm, right? Recall, classical algorithms, they don't have this nice primitive where they can query the oracle in superposition. So if they want, f on the all zero input and f on the all ones input, they have to query it twice. And they show that any classical algorithm requires something like 2 to the n over 2 classical queries in order to solve this problem. So this sort of huge exponential separation between or I guess even infinite separation between the two. But you might look at this separation initially and say, okay, this is a pretty large separation, but perhaps there's an even larger separation, right? Perhaps there's a constant or an algorithm that has exactly quantum query complexity 1, but has classical query complexity 2 to the n, the maximum possible separation that you could hope for. But in fact, this is not true. So any quantum query algorithm that only queries the oracle once can be simulated by a classical algorithm that has something like 2 to the n over 2 queries. So this is really sort of witnessing correlation is really witnessing sort of like the maximum separation you could have. But you could hope to bootstrap this in some ways. And one way you might hope to do that is by defining what's called the k-fold correlation. So instead of having two Boolean functions, f and g, interleaved by these layers of Hadamards, you can have Boolean functions f1 up to fk also interleaved with Hadamards. And this is called the k-fold correlation problem. And once again, if you sort of know the trick for reducing the two queries down to one query for the original correlation problem, it's sort of simple to show that you can reduce this k-fold correlation problem down to something that can be solved with k/2 quantum queries. And so then the question becomes, well, sort of how quickly can a classical algorithm solve this k-fold correlation problem? And indeed, also Aronson and Binus also show in this same paper an upper bound of something that looks roughly like 2 to the n times 1 minus 1 over k classical queries for the k-fold correlation problem. And I started this slide by saying that Forrelation was sort of one of the hardest problems. So this is the upper bound on the number of queries, but is there a matching lower bound? And in fact, that was proved recently by Bansal and Sinha, and also Shirstoff and others have a very similar result, showing that k-fold correlation actually does require something like 2 to the n times 1 minus 1 over k classical queries. And so once again, this is sort of witnessing sort of the maximum separation you can have with k/2 quantum queries. I think I failed to mention that once again, this result was proved for general like k/2 query algorithms. So any query algorithm that has k/2 queries can be solved with 2 to the n times 1 minus 1 over k classical queries. So moving away from some quantum query complexity, if you just sort of think of general quantum time complexity, then Aronson and Binus also show that this k-fold correlation problem is BQP-complete. So once again, sort of another witness of hardness. So that's sort of a brief background on the Forrelation problem, and I think this is one of the reasons that.
Sorry, sure. Can I ask you a question? What exactly does it mean to say that such an oracle problem is BQP-complete?
Yeah, that's a great problem. Great question. So just instantiate these functions, which is sort of like polytime explicit circuits, and that'll be good enough.
Like classical reversible circuits?
Sure. I think that should work. Yeah. So this is actually not so surprising, right? We know that the Hadamard and Toffoli gates are universal, right? So just by interleaving Hadamards and Toffolis, you should be able to get you should be able to get universality in the computational sense.
And are you thinking here of a constant k or a k that's like polynomial in little n?
We're thinking of a k that's polynomial here.
Okay, yeah, that makes sense. Thanks.
It could be true for constant k, but we don't know. So really the only trick here is to show that if the Hadamards weren't applied to literally every qubit, then this would just be completely trivial. So you just somehow have to make sure that even when you apply Hadamards to every qubit, everything still works out. But it will.
Thanks.
Okay, so what are the actual results that we have in this paper? So the results come in sort of two flavors. In the first setting, we treat f and g sort of once again as black box oracles. And we actually will be caring about the time complexity here. So let's just assume that every time we query f and g, it just sort of takes a unit time. But we don't really care what they're doing. They could be doing sort of arbitrarily complex things. Then we show that there's a randomized classical algorithm for Forrelation, which uses something like 2 to the n over 2 queries, which shouldn't be surprising to you because that's what we saw on the previous page, but also uses something like 2 to the n over 2 time. And this is a quadratic improvement in the time complexity of sort of the previous best algorithm, which was sort of noted by Aronson in 2010. So that's the setting, the simplest setting of just two functions. For the k-fold Forrelation problem, we also have an improvement. So on the previous slide, I was sort of obscuring some complexity in the prefactors to this 2 to the n times 1 minus 1 over k sort of dominant term here. There's also terms in terms of k and epsilon. And we improve the query complexity, we improve these prefactors quite dramatically. So for instance, you see here that the improvement in k is something like is an exponential improvement. And there's sort of an unstated extra benefit of our theorem, which is that it's a bit more easy to understand than the original Aronson and bias proof. So so those are the two theorems in the black box setting. But actually, unless there are questions, we won't actually talk much more about these two theorems for the remainder of the talk. I'm going to try to sort of state formally and prove to you the following theorem, which is in a different setting in which f and g are provided as explicit functions defined over some graph. So sort of one informal way of stating this theorem is that there's a polynomial time randomized classical algorithm for correlation when the functions are defined over a planar graph. So, you know, there's a couple things to note sort of right off the bat. The first is that it's a polynomial time algorithm. So notice that the two theorems I've written above are both exponential time. So this is, you know, we're just like in a completely different regime here. And second of all, you know, there's something about a planar graph here. So we're going to need to use something about sort of some algorithmic graph theory techniques in order to get this result. Okay. So perhaps before I go on, are there any questions up until this point? Well, if there are, just feel free to shout them out, and that'll be fine. Okay, so what are these? So the first most important thing is, what are these explicit functions that we've defined over a graph? So these we call them two local functions. So you start with a graph, you place a variable at the vertex, at every vertex of the graph, and then a two local function is simply a product of clauses involving either variables that only depend on a single vertex, or variables that have, or clauses that have variables that depend on either vertex at the end of an edge. So we have the clause we have these vertex variables, and we have these edge variables. So that's the definition. So maybe it'll become more clear with a simple example. So imagine we have this function which assigns 1 to every vertex variable, and assigns -1 to every edge variable, where the variable assignment on either side of the edge is different. So if we look at some assignment to x, say, is of 0s and 1s, then the only non-identity terms are those edges which would go from a variable that's assigned 0 to a variable that's assigned 1. So this is somehow like inducing some kind of cut in the graph. And then it's simple to see that this two local function is just computing the parity of the number of edges in the cut. So this is sort of a simplified example of a function that we'll see later, but maybe it goes to show you that, you know, these two local functions can sort of capture some interesting things. Okay, so now that I've just sort of, you know, formally defined what a two local function is, I can sort of peel back some of the complexity on this theorem. So now we can say there's a classical randomized algorithm to compute the correlation of these two local functions defined over planar graphs in time that scales like n squared over epsilon squared, where n is the number of vertices of the graph. And so there's a couple of things that I want to point out about this theorem. First of all, is that the correlation that we prove here is actually a slightly generalized version of the correlation. Instead of having the layer of Hadamard's between our two Boolean functions, we can actually replace that with a layer of single qubit rotations. These operators, they just have bounded norm. And secondly, the actual condition is not just that it's a planar graph, but rather it's any graph which can be partitioned into two subgraphs of constant Treewidth. And for some of you, this may sort of demystify this part of the theorem. For some of you, it may not, but I will sort of dig into this much more later. So if that doesn't make sense to you, hopefully it will later. So before I actually go on to sort of prove this theorem, then I wanted to give you an application of this graph-based correlation with these two local functions. And the application will be to the quantum approximate optimization algorithm, the QAOA, which I'm sure most, if not all of you, have run across in some form or fashion before. But I'm just going to sort of recapitulate it here on this slide. So this is a heuristic algorithm where the goal is to maximize some classical cost function into the reals. And for our purposes, recall that we're dealing with these sort of graph-based correlation instances, right? These functions defined over graphs. So let's also assume that our cost function is defined over some graph, right? So the cost function is just the sum over these clauses involving the edges of a graph, where these JUV terms are here are just sort of arbitrary real coefficients. And then QAOA works in the following way. First, you promote your cost function to a Hamiltonian. And then you maximize the energy of that Hamiltonian with respect to some class of variational states. And this is, in some sense, the sort of whole name of the game. The richer your class of variational states, the more accurate your estimation will be of the maximum. And then finally, if you have a quantum computer, you take the state that you obtained in the second step, you prepare it on a quantum computer, you measure it in the classical basis, and you obtain some solution, and you output that solution as the solution to C. And so what are these variational states? So these variational states are sort of, they're parameterized by this parameter P, which means that there's these P layers of these two operations. So this first operation, this e to the minus I beta b, is just a layer of single qubit x rotations. And then this e to the minus I gamma c is just, you're applying your Hamiltonian C as a unitary. And one way that you can sort of make sense of the QAOA algorithm is that sort of in the limit, when P is like poly n, that this decomposition here looks like a sort of trotterization of the adiabatic algorithm. So that's how you can sort of prove that when P is large, this algorithm is doing something well. But sort of unfortunately, the problem is that this second step is really the bottleneck. Like, we really only have general classical algorithms which can compute this maximum energy and solve for this state when P is 1. And that's not very satisfying, in particular because it's been shown that, at least in some restricted cases, P equals 1 is sort of a provably suboptimal solution. And so one of the things that we do in this work is to show that calculating level 2 variational energies reduces to this graph-based correlation problem. So if the graph-based correlation problem is efficient, which we'll show later on certain well-structured graphs, that means we can also calculate these level 2 variational energies of the QAOA algorithm. So that's all I'm going to say about that application. And for the rest of the talk, I'm just going to try to sort of prove and describe this algorithm to you. So how might that go? So recall our goal is to estimate this Forrelation quantity. And the proof is going to go into 3 steps. First, we're going to partition our observables into 2 sets, A and B. So I've just sort of rewritten exactly what I had in the goal here, where I've grouped all of the observables in set A and on the left-hand side, and I've grouped all of the observables in B on the right-hand side. So I've done nothing. I've just rewritten the state. And then I'm going to write this as an inner product of states alpha and beta, where alpha contains all the observables in A, and beta contains all the observables in B. So once again, I'm just rewriting what this correlation is. And to make sure that these are actually states, let's just assume for right now that all these observables are just Hadamard gates. It's not too difficult to go to sort of general permission observables, but let's just assume for simplicity now that we're in the original setting where all the observables are Hadamards. And so these will actually be good normalized states. And then in the second step of the proof, we want to show that we can compute certain properties of these states efficiently. In particular, we want to show that we can compute inner products with computational basis states, so computing amplitudes. And also, we want to show that you can sample from sort of a z-basis measurement to these states efficiently as well. So if we can compute these inner products and do the sampling problem, then we can apply this Monte Carlo simulation method of Van den Est to estimate this inner product. And sort of, I want to start with this final step here because it's actually very nice and simple. And maybe if you take nothing else away from this talk, you have this nice little trick that you can apply in your work. So what is this this estimation method for estimating inner products? So this is our goal. We want to estimate the inner product of alpha and beta. And we're going to consider some random variable where we have the inner product of beta and x over the inner product of alpha and x, where x is drawn according to this z-basis measurement of alpha. And so recall that these are sort of all the primitives that I said on the previous slide we were able to do. And so now let's just calculate the expectation and variance of this random variable. Well, the expectation, we can sort of write out the probability. We can expand out this probability. These alpha x's will cancel. And we're just left with the inner product of alpha and beta. And in the second step, we can just look at the variance. We can say the variance is bounded by sort of the second moment of the absolute value. And once again, these alpha x terms will cancel. And so we just get the sum of the squares of the amplitudes, and which is of course 1 because beta is a quantum state. And so now we just have this nice random variable that has the expectation we want and a nice bounded variance. So we can just apply Chebyshev's inequality, which says that something like an empirical average of 1 over epsilon squared samples suffices to obtain an additive epsilon approximation to this inner product alpha and beta, which is the thing that we wanted to estimate. So that's the entirety of this Van den Nest inner product algorithm. And so that may give you some sense of where we're headed. But sort of there's this elephant in the room, which is, how do I actually do this? In particular, how do I choose these sets A and B such that this second step can be done efficiently? So for some choices of the sets A and B, the second step will be or might be efficient, and for some choices of A and B, it won't be, or at least we don't know. So let's take a look at one of these terms in the second step more closely. So let's look at the term where we have the inner product between a computational basis state x and the state alpha. And I've just sort of written alpha here as expanded it as the sum of this two local function over some graph. So let's say that the two local function is acting on this graph on the right here. And this is, in this first step is just sort of the definition of alpha. And in the first step, I'm just going to sort of rewrite things where I've partitioned my vertices according to the sets A and B. So I have this, the vertices in A and the vertices in B. And notice that there are no Hadamard gates, which are applied to the vertices in B. And so this XB term here is basically going to force all of these YB variables in the sum to be equal to XB, right? So in some sense, what we're doing here is we're just taking all of the XB variables and we're sort of fixing them to some fixed value, which sort of removes them from the graph, right? So for the purposes of this inner product, like what really matters are sort of how this function behaves on the graph, which is induced by the vertices in A. And if we do a couple more lines of algebra here, we see that in fact, the function that we get is itself a two local function over the vertices in A. And so what we've sort of shown in this calculation is that in order to compute the inner product between alpha and x, all we need to do is we need to be able to sum over all possible inputs to some two local function defined over a graph. So this is the reduction that we have. And now the only question is, what property of a graph allows you to do this quickly? What property of a class allows you to quickly compute the sum of a two local function over all its inputs? And I claim that that property is Treewidth. And so this is going to require a little bit of a digression for those of you who haven't seen it or need a refresher. So we're going to take our graph and we're going to sort of make it into a tree in some way. And the way we're going to do this is by a tree decomposition. So basically what happens is we're going to take all of the vertices in the graph and we're going to arrange them into sets that form a tree. So on the left here, I've drawn some arbitrary graph. And on the right, I've drawn some tree decomposition of that graph. And one of the things that you'll notice sort of right away is that, the nodes of the tree decomposition contain, the vertices of the graph, but the vertices, they may appear in more than one one bag here. So it's not merely a one-to-one correspondence between the nodes of the tree, which are called bags, and the vertices of the graph. So what are the properties of this tree decomposition that make it a useful sort of algorithmic data structure? Well, first we need some sort of non-triviality condition that every vertex must appear in some bag. So every vertex of the graph must appear in some bag of the tree decomposition. That's fairly straightforward. Similarly, another sort of property which is capturing the structure of the graph is that every edge must appear in some bag. So for instance, if we look at this edge AB in the graph on the left, then we see that there's some bag of the tree decomposition which contains both the vertices A and B in it. Similarly, if we look at another edge, say E and G, there's some other bag that contains both the vertices E and G in it. And then finally, sort of the most sort of challenging condition to sort of wrap your mind around when you first encounter tree decompositions is that for every vertex of the graph, the bags containing that vertex in the tree decomposition form a connected subtree. So if we look at, say, the vertex C in the graph on the left, and we look at all of the bags containing the vertex C in the tree decomposition, we see that that forms a connected subtree of the graph. Similarly, if we look at the vertex E, all of the bags in tree decomposition containing E form a connected subtree. And it will turn out, and we'll see this later, that tree decompositions are useful whenever the bags can be made to have relatively small size. And so we call the width of a tree decomposition the size of the largest bag, sort of -1 for historical reasons. And we'll say that the tree width of a graph is you take sort of the best tree decomposition of that graph possible, and you take the width of that tree decomposition. So it's the min-width tree decomposition. So this is the definition of tree width and tree decompositions. And when you first sort of encounter these things, it's sort of hard to work with. And I don't claim to get you all the way there in this talk, but maybe some examples might be useful. So first and foremost, like a tree is very like a tree, so it should have tree width which is small, and in fact it does, right? So it has tree width 1. A clique is a graph which is very unlike a tree, so it should have large tree width, and in fact it does have tree width n-1. So basically this is saying that the tree decomposition for the complete graph is like basically the only thing you can do is take all of your vertices and put them in a single bag together. That's all you can do. And so that's not very interesting. Slightly more interesting is the grid graph, which has tree decomposition with width square root n. This is not too hard to convince yourself of. You can sort of see that if you take all the columns of the grid graph, you can sort of collapse them down into single points, which have sort of points that have square root n vertices in them. And you can connect these square root n vertices in a path, and this will form something like a tree decomposition. That's sort of one little thing you need to do. But so that will form a tree decomposition of a grid graph, which shows that it has tree width square root n. And at first you might think, well, this is sort of a very specific property of a grid graph, but in fact, it's not. All planar graphs emit a tree decomposition with width square root n. And in fact, these tree decompositions can be found efficiently as well. So I claimed before that the sort of summation of a two-local function depends on the graph's tree width, right? But recall when we did this calculation, right, what we were actually doing was we were taking a partition of the graph, right? We were partitioning into the sets A and B, and then we were looking at sort of the graphs induced by those two sets of vertices. And so what the goal really is not to minimize the tree width of the entire graph, but rather to find a partition for which each half of the partition has small tree width. So that's our goal here. We want to minimize the tree width of each partition. And a priori, you may think that this is not very useful, right? Because maybe if the graph has some sort of global structure, if we split it up into two halves, then the tree width of each half may roughly resemble the tree width of the whole graph. But in fact, to sort of extinguish that intuition a little bit, if you think of a bipartite graph and you take each side of that graph, then you could start with a very complicated graph, and then you immediately get two partitions which don't have any edges whatsoever, and so the tree width is very simple. It's constant, it's 0. But a slightly more interesting example of this comes from planar graphs. So it turns out that every planar graph can be partitioned into subgraphs of Treewidth 2. So this may look a bit mysterious at first, but the proof is actually very nice and simple. So I'll sketch that now. So imagine that we start with some planar graph, and I'm going to give you a partitioning of the vertices. So first, you take your planar graph and you look at all of the vertices on the the outside edge of the graph, and you put them into one partition, and then sort of put those vertices to the side for a second and look at the remaining graph, and take all the vertices on the outside of that graph and put them in the other partition. And so sort of recurse in this way. And what you see is that the partitions that you get are roughly like these concentric sort of circles where sort of one layer of the partition is separating the other layer from itself. And so what you get is that every partition is just essentially a collection of cycles. And it's not too hard to convince yourself that the cycle graph has Treewidth 2, right? So the cycle is like one of the minimal graph, which is not a tree, right? So if you remove any vertex of the cycle, then you immediately get a tree, which we know has Treewidth 1. And so then you just sort of insert that vertex back into every bag. Then you've got the cycle graph again. And so now you've shown that you have a tree decomposition of Treewidth 2. So that's the sort of the sketch for why planar graphs can be partitioned into small Treewidth bits. And so here's our proof outline again. So now we sort of know what we're going for. We want to partition our vertices into two sets, A and B, that have small Treewidth. And eventually we're going to apply this Monte Carlo simulation algorithm of Van den Est. And sort of the only thing I have left to do is to do the second step. And recall that we've already shown a few slides ago that computing these inner products reduces to computing the sum of a two local function. So now for the sort of rest of the talk, I'm just going to talk about sort of taking the sum of two local functions over small Treewidth graphs. And
can I ask a question about step 2?
Yes, please.
The first item of step 2. So for which axis do you actually compute those two inner products? You can't do it for all because that will be time 2 to the n. You haven't sampled anything yet. So which axis do you treat there?
Well, so from the Van den Est algorithm, right, you sample an x, and for that particular x, that's the one that you compute the inner products for.
But then should those two steps, the two sub-steps of step 2 be reversed?
They should be reversed, but the second step is more complicated than the first step. So it looks a lot like the first step. So the way that we're going to do the sampling is by well, the way that we do the sampling is by computing marginals. So we look at the marginal of the first bit, we sample that bit, and then we look at the marginal of the second bit, condition on the first bit, and so on, and do that. And so these calculations are more complicated, but they look very similar to the calculations of just computing the inner product of x and alpha.
I see. Thanks.
I'll show later that the way that we're doing the sampling is actually probably suboptimal, but I'll get into that a little bit later. But yeah, so that's the final point I was going to make on this slide is that yeah, the sampling is accomplished by calculating marginals, and so this is going to sort of introduce an extra factor of n into our algorithm because we have to do this n times for every bit of x. But Ronald's right. Yeah, we should. Yeah, you sample x first, and then for that particular x, you compute these inner products. Okay, so I'm just going to show you sort of one way of doing this. So, doing graph operations efficiently over low Treewidth graphs has been studied sort of extensively, but I'm just going to sort of give you one possible proof of this fact here. So I'm going to break it up into sort of two steps. So in the first step, I'm going to imagine that the two local function that we want to sum over is actually a tree. So there's nothing complicated going on about it, but let's assume that the variables are no longer binary, but they come from some arbitrary alphabet gamma. So I've sort of made the problem simpler in some sense by making it over a tree, but made it more complicated in some sense by making the variables over a larger alphabet. And so just to recall, so this is the exact setting that we're in. We have some two local function x, and we want to sum over all possible inputs to that function. And the proof is very simple. So the proof idea is basically you take a leaf vertex and you sum over all of the possible values to the variable at that vertex. And this is going to correspond to a new tree where we sort of contracted that edge. And the reason this is true is because you can simply take all of the terms of your two local function that contain sort of that vertex and sort of push them as far to the right as you can. And so then the two local function will sort of factorize in this way. And so in this way, you can sort of prove inductively that this will give you the right thing. So how long does this procedure actually take? Well, we see here that the sum here, if we're sort of doing this operation recursively, takes something like gamma time, because there's gamma many terms in the sum. But if these functions are arbitrary, we may not have any better way of storing this information than just storing this for every possible x. So there are gamma possible many values of x, each taking gamma time. So one of these collapse steps takes time that looks like gamma squared. There are n nodes in the tree. So computing the sum takes something like time n times gamma squared. So that's just a very, very simple setting where the two local function is an actual tree over an actual tree. Now let's sort of generalize this to the setting where the two local function is over a sort of arbitrary graph, but you're sort of promised that it has small tree width, some small tree width W. In fact, okay, the tree width could be large, but then the algorithm won't be very useful. Okay, and the proof idea is basically to reduce to the previous slide. So we're going to define a new two local function over the bags of the tree decomposition, where the sum over all of the inputs to the new two local function equals the sum of the variables, the sum of over all the variables to the original two local function. And recall that the tree decomposition is itself a tree, right? So this is why we're using this previous step, because the tree decomposition is itself a tree. So what is this new two local function Q that we're defining? We'll recall that the bags of the tree decomposition have these vertices in them, right? They have multiple vertices in them. So how do we assign values to those sets of vertices? Well, we'll just do it in the sort of the most naive way possible, which is just by assigning every variable within the bag a particular setting. So for instance, this bag on the bottom left here, ABC, could have been assigned 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on and so forth for all the possible combinations. But I've just written some possible setting of the variables here. But recall from earlier, you may immediately see a problem here, right? Because more than one bag contains the same vertex, right? So we see here in this example that the vertex C has been assigned 0 in the bottom bags, but has been assigned 1 in the top bag. And there's no sense in which this variable assignment here corresponds to a variable assignment to the original two local function, where the vertex C would only be assigned one value, either 0 or 1. And so sort of the first step of the two local function, the first thing the two local function is going to do is going to use these edge clauses to enforce consistency on these variables. So if either end of a bag shares a variable, then the two local function Q is going to be 1 if those variables agree on the overlapping variables, and it's going to be 0 otherwise. So for any assignment to these variables that doesn't have variables that agree, the two local function is just going to contribute nothing. And you might wonder, like, why does this even work, right? Because the variables appear in multiple bags, but recall that the bags containing a vertex form a connected subtree. So if we only do these local checks, because all of the bags containing C form a connected subtree, these local checks are enough to enforce global consistency. And so we're sort of crucially using that property of a tree decomposition here. So once we have these edge functions in, we know that any non-zero assignment to the variables over Q will be equivalent to some assignment to the variables in H. And so sort of now all we have left to do is to actually, put in the information of x or of h into this new two local function Q. And the way that we're going to do it is recall that, h is a product of vertex clauses and edge clauses. And so for each one of these clauses in the two local function h, we're going to sort of associate it with one of the bags of the tree decomposition. So let's sort of see how that might look like. Well, so let's take a vertex clause of the two local function. Well, we know that every vertex must appear in some bag of the tree decomposition. So there'd be some bag of the tree decomposition, which we can associate this vertex clause. Slightly more complicated, that also has edge clauses in the two local function. But once again, a crucial property of the tree decomposition is that every edge also appears in some bag, which means we can associate the clause HDE with this bag that contains both the vertices D and E. And so once we've done these two steps, we've done everything. So every assignment to the variables in Q corresponds to assignment of the vertices of the original graph. And we've incorporated all of the various clauses in the two local function H into our new two local function in Q. And so if we sum up over all of the variables in Q, it'll be equal to all of the sum of all of the variables for H. And so we can reduce sort of to the previous slide and obtain an answer. So sort of putting this all together now, if we sort of go through the math of what the algebra of what the running time is at the end, we get a classical randomized algorithm which solves the graph-based correlation problem to additive error epsilon in time that looks like n squared over epsilon squared, where there's now this exponential factor in the tree width of the partition. And as a corollary, we saw before that a planar graph could be partitioned into two subgraphs that had constant tree width. And so this reduces to a solution for the graph-based correlation problem on planar graphs that has time n squared over epsilon squared. So that's sort of the entirety of the proof and the algorithm. So let me just talk about sort of a few remaining open questions and avenues for future work here. So I mentioned earlier that this dependence, the sampling step, the thing we're doing where we're computing these marginals over and over again to do the sampling might not be optimal. Indeed, I gave this talk to a friend and longtime collaborator, Luke Schaefer, and he noticed that you could use sort of a technique from a previous paper of ours, actually, to probably, we haven't written out all the details, but probably do this sampling task more efficiently. So we can actually do the sampling task in something that takes like n times something that's exponential in the tree width. And so this would reduce the entire time of the graph-based correlation problem to something that's not quadratic in n, but linear in n. So now we have an algorithm which is probably linear in n, but still quadratic in epsilon. And so for the second open question, the question is whether or not you can reduce this 1 over epsilon squared dependence to something that looks like a 1 over epsilon dependence. And we actually did quite a bit of work in this paper on simulating, implementing this algorithm in practice. And it seems like, this 1 over epsilon squared dependence is really the thing which is killing us for these applications. So if we could reduce that, that would really be great. And then finally, sort of a last sort of maybe more speculative open question for future work is whether or not this technique could be used to show quantum advantage with efficient classical verification. So what might that look like? Well, recall that the classical algorithm, in order for it to work efficiently, it needed to have some partition of the graph, which each half of that partition had small tree width. But imagine you generate some graph and you obscure it in some way where it has a secret partition which has low tree width, but it's sort of algorithmically hard to find that low tree width partition. Then if you give this to some device which is claiming to be quantum, if they solve it efficiently, right, or quickly, then you might say that this is evidence that they actually are a quantum computer, because recall that a quantum computer doesn't need to know any structure of the graph in order to solve the Forrelation problem. It just sort of applies it to the uniform superposition and samples. And so if it's coming back quickly, then you might say that this is evidence that it's actually computing this graph-based correlation. And of course, you can then verify it because you know the secret partition that you generated. And so you can actually test to see if it's giving you the correct answer. Okay, so maybe with that, I'll end there and stop for questions.